this session, we discuss about noise figure, noise temperature, and system temperature concept. Noise figure F relatives the SNR at the input of the network to the SNR at the output of the network. The noise figure means the SNR degradation causes by the network. Here, the below figures explain. The below figures displays the SNR at amplifier input SNR in as a function of frequency. At its peak, the signal is 40 dB above the floor noise. The figures depicts the SNR at the input at the amplifier output SNR out. The amplifier gain has increased by signal by 20 dB. However, the amplifier has added its own additional noise. The output signal and its peak is only by 30 dB above the noise floor. Since the SNR degradation from the input and output is nearly 10 dB. This is 10th amount of the describing the amplifier as having a 10 dB noise figure. Noise figure is a parameter that expresses the noisiness of the two-port network or device, such as amplifier compared with the reference noise source at the input port. It can be written as, that is, noise figure F is equal to SNR of input divided by SNR of output. That is equal to SI by NI, that is signal to noise ratio of the input whole divided by G into SI by G multiplication by NI plus NAI. In the above equation, SI is equal to signal power at the amplifier input port. NI is equal to noise power at the amplifier of input port. NAI indicates amplifier noise referred to the input port, and the value of G is indicating gain. In the below figure is an example to explain and represent realizable amplifier. Example, with a gain of G is equal to 100 and internal noise power NA is equal to 10 microwatt. The source noise external to the amplifier is NI is equal to 1 microwatt. The figures, we assume that amplifier is an ideal and we describe the noisiness of the real amplifier as a part A figure. To an external noise NAI in series with the original source NI. The value of NAI is obtained by reducing the NA by an amplifier gain, as shown in figure 5.15. The above equation reference with all noises to the input amplifier input, whether the noise is actually present at the input or is internal to the device. As we can see in the figure 5.15, the noise power from the real amplifier is identically that electrical equivalent model. It is reduces to F is equal to Ni plus NAI divided by Ni, that is equal to 1 plus NAI divided by NAI. Notice from the equation above, that is the noise figure expresses the noisiness of the network relative to an input noise source, noise figure. Noise figure is not an absolute measure of noise. An ideal amplifier or network, one that contributes no noise, has no figure equal to unity, that is equal to 0 dB. For the concept of noise figure, have to utility we need able to make equitable comparison among devices on the basis of equation 5.26. We must therefore choose a value of Ni as a reference. The noise figure of any devices will then represent a measure of how much of noises the devices is then reference. In 1944, Ferris suggested a noise figure to be defined for a noise source at a reference temperature at 290 degrees Kelvin. That suggestion was subsequently adopted by IEEE as a part of standard definition of noise figure. From the equation, we seen that the maximum available noise power spectral density from any source resistance is established by specific its temperature. The value of 290 degrees Kelvin was selected as a reference because it is reasonable approximation of the source temperature for many links. Also, we with temperature chosen to be 290 degrees Kelvin, the value of noise spectral density N naught at a temperature T naught results the aesthetically pleasing number, that is N naught is equal to K T naught, that is equal to 1.38 into 10 to the power of minus 23 into 290, that is approximately equal to 4 into 10 to the power of minus 21 W per Hs. Is this expressed in decibels, that is minus 204 W watt per Hs. Now, the noise figure F has been divided with the reference at a 290 degrees Kelvin noise source. It is important to emphasize the noise figure relationship in equations. And 5.25 and 5.26 are only the accurate when Ni is 290 degrees Kelvin as a noise source. For those cases where Ni is other than 290 degrees Kelvin, we must rename F in equations 5.25 and 5.26 to be termed as a operational noise figure, that is F of. The relationship between the F of and F is shown in next part. Now coming to the next topic, noise temperature. Based on the above equation, we can rewrite Fnai is equal to F minus 1 into Ni. From the equation 5.16, we can replace Ni with K T naught W and Na with K Tr W, where T naught is the reference temperature of the source and Tr can be called as the effective noise temperature of the receiver. So we can write as K T naught W is equal to F minus 1 K naught into W. That is Tr is equal to F minus 1 into T naught, or T naught has been chosen be 290 degrees Kelvin. Tr is equal to F minus 1 290 degrees Kelvin. In the equation of 5.26 uses the concept of noise figure for the characterizing the noise of an amplifier. But in equation 5.28 we represent a relative but equivalent characterization known as effective noise temperature. Note that noise figure is a measurement relative to the reference. However, noise temperature has no such a constraint. We are thinking of available of noise spectral density and effective noise temperature in the above equation. As the equivalent ways of characterizing the noise sources, the equation tells the noiseless of an amplifier can be moduled as if it is were caused by additional noise sources operating at some effective temperature called Tr. For a purely resistive termination of Tr, Tr is never less than ambient temperature unless it is cooled. It is important to note that For relative terminations such as uncooled parametric amplifiers or other low loss devices, TR can be much less than 290 Kelvin, even though the ambient temperature is high. Then the output of the amplifier as a function, its efficient temperature, we can calculate again the value of a N naught, that is equal to GNI plus GNAI. That implies GK T naught W plus GK T naught R plus W. TRW. If you common G into K as a common, TZ plus TR into W. That implies GK TZW plus, based on the above equation, the value is replaced by F minus 1 GKR T naught into W. So here we get the final equation GK TZW plus F minus 1 GK T naught W, where Tz is the temperature of the source and T naught is equal to 290 degrees Kelvin. So we can conclude that the effective noise temperature along with the figure of noise with respect to temperature. Now we are moved to the next concept, line loss. The difference between the amplifier network and lossy line network can be viewed in the contents of degradation mechanism, loss and noise. Described we are earlier, noise networks in the above section we discussed with amplifier in mind. Now we saw the SNR degradation results from the injecting additional noise into the link. However, in the case of lossy line, we shall show that the SNR degradation results from the signal being attenuated while the noise remains fixed. For the case where the line temperature is equal to or less than the source temperature, the degradation effects will nonetheless to be measured as increasing in the noise figure or effective noise temperature. Consider the lossy line or network shown in 5.16. Assume the line match with its characteristic impedance at the source and at the load. We shall define power loss L is equal to input by output. Then the network gain G is equal to 1 by L. Let all components, the temperature Tz, the total temperature out, power flowing from the network into the load is N out is equal to K T naught into W, we expressed in the above equation. Since the network output appearance as pure resistance at the temperature Tz, the total power flowing from the load back into the network must also equal to N out to ensure thermal equilibrium. Recall that available noise power dependent on temperature, bandwidth and impedance matching. It is not depends on resistive value. And N out can be considered to be map up two components, Ng and Gn, such that N out is equal to KTGW, that implies NGO plus GNL, and NGO is equal to KTTZ into W. In the component of output noise power due to the source, and GNL is the component of output noise power due to the lossy network, where NL is the network noise relative to the input. By combining above two equations, we can write as KTZW is equal to ZKTZW plus GNL, and we solving NL else NL is equal to 1 minus G whole divided by Z multiplication by KTZ into W. That implies KTLW. Therefore, the effective noise temperature of the line TL is equal to 1 minus G whole divided by G into Tc. We know that since G is equal to 1 by L, that implies TL is equal to L minus 1 into Tc. Choose Tc is equal to 290 degrees Kelvin. The reference temperature we can write as TL is equal to L minus 1 into 290 degrees Kelvin. By the above two equations, we can conclude that the noise figure of a lossy line can be expressed as FL is equal to 1 plus TL divided by 290, that is equal to L, where the network is a lossy line, such that F is equal to L, G is equal to 1 by L, and the N naught equal to KTZW divided by L plus 1 minus 1 by L KT naught into W. Note that some other authors use parameters L mean the reciprocal of the loss factor defined here, and in such cases the figure of merit is equal to 1 by L. Now let us consider three examples to calculate the figure of merit for different types of lines. First of all, we consider the lossy line. See the problem. A line temperature T0 is equal to 290 degrees Kelvin is fed from a source whose noise temperature is 1450 Kelvin. The input signal SI is equal to 100 picowatts and the signal bandwidth W is equal to 1 gigahertz. The line has a loss factor L is equal to 2. Calculate the SNR of input, the effective line temperature TL, and the output signal S out and the SNR out. We know that from the noise figure equations, input noise Ni is equal to KTZ into W. And all parameters are given in the problem. Replace K value, that is the Boltzmann constant, and Tz, that is 1450 Kelvin, and the value of a bandwidth is equal to 1 gigahertz, that is 10 power of 9 Hz. So you will get the value of input noise is equal to 20 picowatts. And after that we are calculating SNR of in equal to 100 picowatts divided by 20 picowatts, that is equal to 5, approximately equal to. After calculating the SNR of input, then we are calculate the value of a TL, that is L minus 1 into 290K, that is 290K. Then S out is equal to SI by L, that is 100 picowatt divided by 2, that is 50 picowatt. From the equation 5.39 we observe that N out is equal to KTZW whole divided by L plus 1 minus 1 by L into KT naught into W. All are known parameters. We know the K value, we know the Tz value, we know the bandwidth value, and substitute all these values here, you will get the value is equal to 12 picowatt. So once we get the value of a N out, then calculate the SNR out, that is 50 picowatt divided by 12 picowatt, that is 4.17. See that SNR of input is equal to 7 dB and SNR output is equal to 6.2 dB. So once we calculate the SNR of in and SNR out, there is a possibility to calculate the figure of merit SNR of in divided by SNR out. They may be extend the question to calculate the figure of merit. This is the one type of example. So coming again to the same problem, he will give in all the parameters. You need to calculate the Ni, and after that we are measure the SNR of in, and after that we are measure the N out, and after that we are measure the SNR out. There may be extend the problem to calculate the figure of merit. We know that the figure of merit, that is SNR of in divided by SNR out. We know that SNR of in value and SNR out value. There may be a possibility to calculate figure of merit value also. And now we are moving to the next concept, that is composite noise figure and composite noise temperature. When two networks are connected in a series, the composite noise figure can be expressed as F composite is equal to F1 plus F2 minus 1 divided by G1, where G1 is the gain associated with the network 1. When the network is connected in the series, the relationship between the stages is expressed to continue, so that the composite noise figure of n stages can be written as f composite or f compound is equal to f1 plus f2 minus 1 divided by g1 plus f3 minus 1 divided by g1 g2 and so on, fn minus 1 divided by g1 g2 and so on, gn minus 1. Can you guess the above equation what the design goals for the front end of the receiver should be? At the front end of the receiver, the signal must be susceptible to add noise. Therefore, first stage should be have low noise figure F1 is possible, and also because noise figure of each subsequent stage is reduced by gain of previous stages. It behaves as strive for such a high gain G1 as possible, simultaneously achieving at lower F1 at the highest G1 represents convince goals. Therefore, compromises is always necessary. The above equations can be combined and expressed as a composite effective noise temperature of n sequences. That means network 1 is connected to network 2 and network 3 is connected to the network 4 and so on. And finally, the output is given to the amplifier. Then T out is also expressed as T1 plus T2 divided by G1 plus T3 divided by G2 plus T3 divided by G1 G2 and so on, Tn divided by G1 G2 and so on, Gn minus 1. The above expression field line in series with the amplifier. There is a typical arrangement of the following receiving antenna. In the equations, we find F compound for the such a lossy line and amplifier arrangement. We can write the particular F compound is equal to L plus LF minus 1, that is equal to LF. Since the noise figure of the lossy line is L and the gain of the line is 1 by L, by analogy with the equations, we can rewrite the composite temperature T composite is equal to LF minus 1 into 290 degrees Kelvin. So we can also write the composite temperature with supporting of amplifier T compound is equal to LF minus 1 plus L minus L into 290, that is equal to L minus 1 plus L F minus 1 into 290, that is equal to TL plus FTR. Make sure that the formula for composite temperature TL plus LTR. Now we are moved to the comparison of noise figure and noise temperature. There is a comparison between noise figure and noise temperature. Since noise figure F and effective noise temperature T0 characterize the noise performance of a device, some engineers feel that compelled to select the one of these measurement is more useful. However, they each having their place. For terrestrial applications, F is almost universally used. The concept of SNR degradation for the application, degradation for a 290 degree source, temperature makes sense because terrestrial sources temperatures are typically close to the 290 degrees Kelvin. Terrestrial noise figure value typically fall convenient range of 1 to 10 dB. For a space applications, T0 is more common figure of merit. The range value for commercial systems is typically between 30 to 150 Kelvin. Giving advocate resolution for the comparing performance between the systems. A disadvantage of using noise figure for such a low noise networks is that the values obtained all are closer to unity, that is lies in between 0.5 to 1.5 dB, which makes it difficult to compare devices. For low noise applications, F would be need to express to two-dimensional places to provide same resolution or precision as does T0. For space applications, the reference temperature of 290 degrees Kelvin is not appropriate as it's for terrestrial applications. When you are when using the effective temperature, no reference temperatures other than is needed to judging the degradation. The effective input noise is simply compared to the effective noise source temperature. In general, the application involving very low noise devices seems to favor the effective temperature measure over the noise figure. And now we are moved to the next topic, that is system effective temperature. In the below figure, we represent a simple schematic of receiving system. It having receiving antenna connected to the preamplifier. A antenna, the line and the preamplifier that plays a primary role in SNR degradation. We have already seen the degradation role of a permeable preamplifier. Additional noise is injected into the link. We have discussed in lossless line loss, the signal is attenuated. While the noise is held fixed, the remaining sources are degrading the steam from both natural and man-made sources of noise and interference that enter into the receiving antenna. Natural sources including lightning, radio sources, atmospheric sources, and thermal radiations from the ground and other physical structures. Man-made noise including radiation from the automobile systems and other electrical machinery, and radio transmission from the other users that falls with the receiver bandwidth. The total noise contributed by the external sources can be characterized and to known as antenna temperature. An antenna, like a lens, the noise contributed are dictated by an antenna looking at. If an antenna is pointed at a cool portion of the sky, a very little thermal temperature is introduced. The antenna temperature is a measure of effective temperature integrating over an entire antenna pattern. We know to find the system temperature by adding together all system noises contributions, and the summation total system noise is equal to antenna temperature noise and the composite temperature of the line and the preamplifier. Two primary sources of noise and interference degradation at the receiver. One source characterized by TA represent degradation from the outside arriving via antenna, and the second source characterized by the T compound, the thermal noise caused by motion of electrons in all conductors. Since the system temperature Ts is now composite made up of TA and composite effective temperature of the line and preamplifier. One might ask, why does the equation appear have same sequential gain reduction factors as those equations? We have assumed that antenna has no dissipative parts. Its gain, unlike amplifier or attenuator, can be throughout of processing gain. Whatever the effective temperature is introduced at the antenna comes through unaltered by the antenna. The antenna represents the source, and source temperature at the input can be written as total Ts is equal to TA plus TL plus LTR. So we can conclude that the LF is provide a unit decibels, we must provide LF as a ratio, so that the Ts is equal to TA plus 10 to the power of LF divided by 10 minus 1 into 290 degrees Kelvin. The above equations describe temperature Ts receiving antenna terminals. The equations describe the power received PR antenna receiving antenna. These are the definitions used throughout the chapters and prefer the system's design, antenna design, and thus working and the transmitter side of the link. It is most important to note that there is another set of definitions used by receiver design who prefer to describe the system temperature and received power at the input to the receiver. Assume that an antenna and the receiver are connected via nothing more elaborated than a lossy line. Then Ts and Ts dash are related to the line loss factor L. That is, Ts is equal to LTS and PR is equal to LPR. When computing these receiving SNRs by using relative reference conditions definitions for the power received and the system temperature, there is no difference in the result compared to the using the original because the factor L appear in the both numerator and denominator of SNR and hence cancel to each other. And we move to the next concept, that is calculation part, noise figure and noise temperature calculation. Already we discussed these topics. Now we can calculate the noise temperature and noise figure by considering some of the inputs as an example. So read the problem. A receiver front end shown in figure below with a noise figure of 10 dB and a gain of 80 dB, bandwidth equal to 6 MHz. The input power SI is 10 to the power of 11 watts. Assume the line is lossless and antenna temperature is 150 Kelvin and calculate some parameters. First we convert all decibel values to the ratios, that is TR is equal to F minus 1 into 290, that is 2610 Kelvin. By using equation L equal to 1 for the lossless is TS system noise is equal to TA plus TR, that is 150 Kelvin plus 2610 Kelvin. Total temperature is equal to 2760 Kelvin. Now we find the value of N naught based on the formula shown in the figure. We will get the 10 to the power of 8 and 1.38 into 10 to the power of minus 23 into 6 into 10 to the power of 6 multiplied by the total temperature. You will get finally source contribution is 1.2 microwatt, front end contribution is 21.6 microwatt, and total is 42.8 microwatt. Now we have to calculate the SNR of in. SNR of in is equal to SI divided by KT naught into W, that is approximately equal to 806.5 dB. And see this, assume no loss, received front end, assume no loss, pre-amplifier and receiver. We are get F is equal to 10 dB, gain is equal to 80 dB and with bandwidth of 6 MHz. With no loss, pre-amplifier F1 is equal to 3 dB and gain is equal to 13 dB and bandwidth is equal to 6 MHz and followed by the receiver. Improving the receive front end with low noise pre-amplifier. And after that we are find out the value of SNR out, that is N out divided by N out, S out divided by N out. You will get 43.9, that is approximately equal to 16.4. So here we notice that example that the amplifier noise is significantly larger than the source noise and represent major cause on SNR degradation. That is the outcome of the above problem. Now we move to the next problem. How do we improve the SNR with low noise preamplifier? So we find is that in the above problem, so the SNR will be reduces by using preamplifier and receiver. Now we are moved to how to improve the value of SNR with low noise preamplifier. See the some used preamplifier as shown in the figure with noise figure is equal to 3 dB and gain is equal to 13 dB with a bandwidth of 6 MHz. To improve the SNR of the receiver, find out a T composite for the composite preamplifier and receiver and find all these parameters. Assume that there is a zero line loss. Again convert all into decibels and proceedings, and TR1 f minus 1 into 290 degrees Kelvin, you will get f1 is equal to 0, that is 290 degrees Kelvin, and TR2 is also equal to f2 minus 1, that is 2610 Kelvin. Now T composite is equal to TR1 plus TR2 divided by Z1, already we expressed in the previous slide, that is approximately equal to 420.5 Kelvin, and TS is equal to TA plus T composite, that is 570.5 Kelvin. Then we are calculate F composite, that is equal to F1 plus F2 minus divided by G1, you will get 2.5, that is approximately equal to 40. And after you are calculate N out by using same formula, apply the known values and get the unknown values. Here we get source contribution is the 24.9 microwatt and the front end distribution is 69.6 microwatt, and overall you will get 94.4, and SNR out you will get 212, that is 23.3. We can conclude that with the added preamplifier, the output noise has increases to 94.4 microwatt. Even though the noise power has increases, the noise system temperature has resultant 6.9 dB improvement in SNR. The price we pay, the improvement is need to be provided for a F composite improve 6 dB. Here, unwanted noise is in part injected via antenna and in part generated internally in the receiver front end. The amount of system improvement that can be rendered via front end design depends on what portion of total noise in the front end contributes. We see in the above example that the front end contributed the major portion of the noise. Therefore, providing a low noise preamplifier improve the system SNR significantly. In the next example, we shown the case where the major portion of the noise injected via antenna. See the example number 3, attempting SNR improving via TA is large. Repeat the same example. Let us TA is equal to 8000 Kelvin. In other words, preponderant amount of noise is being injected via antenna. The antenna must have a very hot body, is fully occupied with a field of view. Calculate the SNR improve that would be improved by the preamplifier used and compare the results. Without preamplifier, we are measuring the value of N out, that is G K W plus TA plus TR. Here we get the source contribution is 66.2 and front end contribution is 21.6. That is approximately equal to 87.8. Now SNR is equal to S out by N out. You will get 11.4, that is 10.60. Now we go for the with preamplifier. N out you will get 20 into 10 to the power of 8 into 1.38 into 10 to the power of minus 23 into 10 into 10 power of minus 6. You will get source contribution is 1324.8 and front end contribution is 69.6. Total is 1394.4 microwatt. And now SNR is equal to 14.4. Therefore, in this case, the SNR improve only 1 dB. A far cry from the 16.9 dB accomplished earlier. When the noise is mostly due to the devices within the receiver, it is possible to improve the SNR by introducing low noise devices. However, when the noise is mostly due to the external causes, improve the receiver front end will not help so much. Now the noise figure is to be definition predicated on reference temperature 290 degrees Kelvin. When the noise temperature on the other hand other than 290, in this case example shown in the above on operational effective noise figure that describes actual SNR versus SNR out relationship. Starting from the all equations, we can finally write that F output is equal to SI divided by KTA naught into W whole divided by GSI divided by G into KTAW plus NAI. After solving all the components, you will get 1 plus T naught by TA into F minus 1. This is the total F opposite F output. Now we are moved to the important topic, that is sky noise temperature. This is our last topic in the noise figure. The receiving antenna collects a random noise emission from the galactic, solar and terrestrial sources. We can be called as a galaxy. Constitute the sky background noise. The sky background appears as a combination of galactic effects that decrease with frequency. The atmospheric effect that start become significant at 10 GHz and increase with frequency. The sky temperature as measured from the earth due to both these effects. Notice that there is a region between 1 to 10 GHz where the temperature is lowest. The galaxy noise has become quite small at 1 GHz, and for satellite communication, the block body radiation noise due to the absorbing of temperature absorbing the atmosphere is not significant below 10 GHz. The region is known as microwave window or space window. In a particular useful for satellite or deep space communication. The low sky noise is a principal reason for such a systems primarily using carrier frequency in a part of spectrum. The galaxy of atmosphere noise shown are made up of family of curves, each at a different elevation of theta. When theta is 0, the receiving antenna points at origin and the propagation path encompasses the longest possible atmosphere layer. When theta is 90, the receiving antenna points to the zenith. And resultant propagation path continues shortest possible in the atmospheric layer. The upper layer of the family represents the nearest worst case sky noise temperature versus frequency. And the lower curve represents most begin case. The figure shown is the plot noise temperature versus frequency due to the rain. Since the intensity of any rain storm can only express it statistically, the noise temperature shown are values exceed 25% on time, which spectral region appears most begin for the space communication. When a rainfall is taken into account, it is the region at the glow end of the space window. For this reason, the system such as Space Ground Link Subsystems or SGLS in the military and Unified S-band Telemetry Tracking and Control System NASA are located 1.8 into 2.4 GHz band. The various researchers have mapped the galactic noise radiations as a function of frequency. In the response, the radio temperature map after K0 and K curves indicating the temperature counters of the sky in the region of 250 MHz. When you view from the Earth, in general, the sky composed of localized galactic sources, each having own temperature. The map effectively weighted sum of individual galactic sources of temperatures, plus as a constant sky background. The coordinate in the map degradation of light ascension can be through as a celestial latitude and longitude with a earth surfaces. The temperature counters range from 90 kelvins to 100 high of 1000 Kelvin. The measurements were made so as exclude sun, night sky, that is night sky. The antenna beam in the center of the map indicates the size of the sky over A which measurements are made. The narrow beam, that final resolution of the temperature counter, wide beam as cursor of resolution. As a reference figures, such a radio map at 600 MHz after pinning tone and terrain. The frequency of galaxy noise is reduced compared in the below figure as represented. At low of 8K and high of 290K, if you are examining these figures for the reason of greatest noise of radiation, where one map do you see most actively and one map it is significantly. It is seen as elongated region in the right hand midsection of each map. The longitudinal axis of elongation, designation and the locations of our galactic plan where such a cosmic noises is most intense. Here we observe the radio map of the sky background at 250 MHz and radio map of sky background at 600 MHz. Till we are discussed the topics regarding about noise figure, noise temperature and system temperature. And we analysis the noise figure with respect to frequency, with respect to input power level, with respect to output power level and with respect to SNR. And after that we measure the figure of merit based upon the noise levels. And after that we are measure the noise temperature. And after that we are measure the line noise. We know that line noise is the ratio between input by output. And after that we are consider the lossy line. After getting the lossy line we are measure the figure of merit, SNR output and SNR input. And after that we are discussing about composite of noise figure and composite of noise temperature. By combination of these two we are getting the new format of equation, that is F compound is equal to F1 plus F2 minus F1 by G1. There is a lot of improvement the particular formula after getting the T component. And after that we discuss the comparison of noise figure and noise temperature. And after that we are realize system effective temperature by considering of a receiver. And after that we are considered three examples. In the first example we are consider noise figure and noise temperature. In the second example we are considering improve the SNR with no noise preamplifier. And the third example we are attempt the SNR improved via value of temperature is lost. These three are the very important examples to analysis the noise temperature and noise figure in the receiving section. And after that we are moved to the sky noise temperature. In the sky noise temperature we analysis the frequency with respect to noise temperature with respect to different variations starting from 10 power of minus 1 to 10 to the power of 10 square gigahertz range, and we are estimate the noise temperature from 10 power of 0 to 10 power of 3. And we are analysis the microwave window, galaxy window, noise due to the atmospheric absorption from the oxygen and water vapor shown in the response. And after that we are analysis radio maps of a sky by considering radio map of the sky background of 250 MHz and a radio background of 600 megahertz. And we finally conclude that here noise temperature, noise figure, and system noise will plays a crucial role at the receiver designing. If you are having a good idea of these particular considerations, we are design a best receiver for wireless communication. So that's why we have to put maximum focus on these noise figure, noise temperature, and system temperature. Thank you.